Good evening, everybody. This is for EE350 Lab 2. We're doing the MATLAB portion of this. So we need to go forth and we're going to be doing this work here in MATLAB. I'm going to be currently using MATLAB 2020B. You can do this basically with any version of MATLAB from 2018, 2017 onward. But for this case, I'm using 2020B. So we're going to need to calculate the following from this question here. So we have our input value, which can be changed in demos as follows. In our case, this is what our values are going to be. We have a three-phase 480 volt circuit that has a positive sequence Y connected source. This applies a delta connected load. The impedance of the lines between the source and the load is negligible. The line on the VAB is 0. And the angle. The phase impedance of the load is 20 minus J 8 ohms. The following outputs should be the following: the phasor values of the line-to-line voltages at the load, the phasor value of the line currents, the phasor values of the phase currents in the source and the load. Calculate the complex power S that is consumed by the load. What is the power factor of the load? So we're using MATLAB to go forth and solve this for us. One key thing is that this is a Y-connected source that supplies to a delta connected load. Those are key points of info. Sorry, a motorcycle just ran by. I hope you didn't hear that. But with that being said, the key thing to get with this is remember that this is a Y-connected source and supplies a delta-connected load. There are certain divine constants that we'll go through and state. That's something to remember. So we're going to go ahead and minimize this and pull up MATLAB. We are going to need to just go through and define some stuff first. We need to CLC clear. We need to clear all. This is mostly just basic MATLAB stuff. We got to go through, make sure everything up. So when we run it, close all. It's going to be EE350 Lab 2. So first we need to just define the variables we're using today. Define. It's going to keep your code neat, cleaned, and commented to make sure you're able to read by other people, not just you. And later afterwards, especially when you go look back at it, it's very important. So V divided V line to line is going to be equal to 0. Our V line to line theta, this is the angle of the V line line, it's going to be 0. We're just defining it right now, so when we do the math later on, it's not just pulling, we're not making it up. V phase is going to be equal to 0. Our V phase theta is going to be equal to 0. Now we're going to go ahead and get our inputs. This is what we had before from our statement from before. So we are going to need this here, you'll see. Our three-phase 400 volt circuit has a positive sequence Y connected source, applies a delta connected load, the impedance values of the line. So this right here, we're going to be inputting our motorcycle. We're going to be inputting another 480 volt circuit in our sequence. So here we're going to define that. Our Z1, this is going to be resistance. It's going to be equal to, I'll capitalize this, is equal to 20 plus 8J. Our VAB, our voltage AB, is going to be equal to 480 volts. The angle of VAB is our source voltage. Is going to be equal to 0. Now we do need to do some equivalencies here. This is just some defined stuff that we'll have. For our circuits, for our circuit and our problem. So we know V line to line is going to be equal to VAB. So when I reference V line, I'm referencing VAB. Our V line to line theta is going to be equal to VA to B theta. Our V phase is going to be equal to our V line to line. and our V phase theta is going to be to our V line to line theta. Now, when I'm stating theta, what I mean by that is our angle of our power, our V phase is going to be equal to that. So next, we need to go forth and do some converting. We need to convert our resistance, our Z, to polar. This is very important for our math. So Z equals to the absolute value of Z1. So what's it's going to do is take the absolute value of this. It's going to get rid of the J. So we'll just left them with the 20. And then Z theta, this is going to be getting our angle of this. We're going to equal to the angle of Z1. We're taking the angle of this. We're going to find the angle of Z1. And then we're going to need to find, this is going to be converting our, basically what we're doing is we're separating the 20 from our, from the front, and then we're taking the 8 and converting that to its actual angle. So here, this is where we're going to be doing rad 2 degrees, this radians to 2 degrees, Z theta. So first we separated them, the 20 and the 8J, and then now we're taking the 8J and converting it to its degrees value. Okay, then from there we can go ahead and run. I'm just going to save this on my desktop. The basic file test. Artiste. Is right here. Use VV line. We have a problem here where unrecognized function VL theta. Oh, oops. That's good to run your code every once in a sequence because you're able to go through and see what's actually wrong with your code. As you can see here, we do have a problem. Oh, absolute value. As you write code, you do tend to forget things as you go along. It's very important to put semicolons to make sure you suppress your outputs. Where else did I put it? Here. Cool. So our VAB should be the correct value. Our V theta is the correct value. Our Z and Z1, this is very important. Our Z and Z1 need to be the correct values. Make sure this is capitalized. Press again. So our Z should be roughly the same correct value, and our Z theta is 21 degrees. Yep, so we're all set. So now we're on the right angle. You can see I'm referencing right here, looking at this, so I know this is correct and that's correct. You can do calculations in your head if you want. Not in your head, but if you're calculating, you'll see. So now after converting Z to polar, we need to get our load delta connection, the load delta connection. So this is where we're defining our load delta connection. So we are going to state that VBC is equal to VAB. This is along delta connection. So we know that the voltage VBC is equal to VA. As stated before, VAB is going to be equal to 480 volts. Then we want to be now with VBC theta, the angle of our VBC is going to be equal to negative 120. So it has a shift to it. And our VCA is going to be equal to VAB. So its voltage is the same, but we can see here also it's going to be shifted by another negative 120. In this case, it's going to be equal to negative 240. Should we suppress? Next, we need to do our source. This is our source Y connected. I'm going to state the constants and just define the values before starting the math. So voltage AN is going to be equal to V line to line divided by the square root of 3. I'm gonna run the code just to make sure we're getting the right stuff. We see here we have a error on line 30. We do have one extra parentheses. So as we can see, working around, and VAN is going to be equal to 277 volts. Next, we're going to do VAN theta. So we're finding the angle of our VAN, and VAB theta minus 30 degrees. So it's going to be subtracted by 30 degrees. Then we're going to do VBN. Is going to be equal to the same thing. So which will be V line to line. We can go and just copy here. Copy and paste it. It's going to be exactly the same calculations. We can basically state that all the voltages are going to be the same for our VABs. And the same thing's going to go here for our VBN. But instead, this time around, it's going to be a subtracted by 120. Like so. Let's go ahead and fix this real fast. There you go. Next in your VCN, it's going to be equal to exactly the same as before. V line divided by the square root of 3. Then as you can see, our VCN is going to be probably equal to something very similar. So it's going to also be VAB theta. It's subtracted by 120. So our source Y connected has been all set. So now we just need to go through and calculate our currents. So everything's been defined and stated, our voltages and whatnot. So now we just need to go through and calculate our I phase. The I phase is going to be equal to the V phase divided by Z. Now remember, V phase, as stated before, is equal to V line to line. V line, which was earlier stated VAB. So we know V phase is equal to 480 volts. And we're calculating divided by Z. Our Z is in our resistance. So this is just a regular Ohm's law. Voltage divided by resistance is equal to current. So we have V phase divided by Z. And our Z in this case was the absolute value of Z1. So this is the magnitude of our polar converted resistance. In that case, our Z is going to be 21.54 divided, so it's going to be 480 divided by 21.54. And after we do that, we're going to be good to go. We're going to go ahead and stop right here and we're going to run it, make sure everything's working correctly. As you can see, our I phase is going to be equal to, you find it here, 22.28. Next, we need to connect to I phase theta. I phase theta is going to be equal to V phase theta minus Z theta. So we're doing the same thing we're doing Ohm's law, what we're doing before, but this time when you do polar division, since we're doing V phase, if this is just handwritten down, not in MATLAB, because we separated our angles for the sake of MATLAB, because it's kind of difficult to do polar additive subtraction and multiplication here. So it's a lot easier just to separate your angles. So in this case, normally you'd have your V phase like 480, angle 0, and Z would be 21.54, and our theta would be an angle of 21.8. And then you divide. So the V phase and Z would get divided, and then our angles would be subtracted. So this is what we're doing here, is it's just subtracting the angles. So next we're gonna be calculating our, after that's done, we'll run it through, make sure it's run. So as we see here, we got our V phase, our angle is gonna be negative because with respect to 0, so our angle just becomes negative. So now we need to get our angles of the currents of our delta connection. So it's gonna be VAB is gonna be equal to V phase divided by Z. So it's exactly the same calculation as before. So it's gonna be the I phase is equal to IB phase. The only thing that's gonna change is it's all gonna change is the angles are shifting. So you can see here the V phase theta, it's gonna be exactly the same calculations as before. The angles are gonna be exactly the same. But for our IBC, the math is, we're gonna have the same magnitude, but our angle is gonna be shifted by 120, just like it's a voltage counterpart. So instead, we are going to take, it was not I phase, I meant to say IAB theta. So now what we're going to do is do exactly the same thing here. We're going to copy this. We're going to take and minus 120. From there, we will get our IBC and IBC theta. So now we get our ICA. That's going to be equal to V phase divided by Z, as done before. I will say magnitude. ICA, current CA theta is going to be exactly the same before. It's going to be, instead, we're going to be shifting by additional 120. So we're just going to take IBC theta and minusing by 20. So if you really wanted to, you could do the same thing. We could take I phase theta, subtract it like we did here by this. We'll take IB theta, we'll subtract out 120, and then here we do 240 if you wanted to, but just for the sake of this, we did this. Run it to make sure, no errors. We see here we did not suppress these. Again, our value should be all correct. So that's all our currents. We do have one more, sorry. We do need to connect our, separate these. We do need to get our IA current, and that's gonna just be square root of 3 multiplied by our IAB. Now for our current A, that's going to be equal to our IAB theta minus 30 degrees. Now for IB, our current B, it's going to be the same thing, but instead our square root is going to be the 3 times IBC. Current will be exactly the same thing, I underscore B theta is going to be equal to I underscore A underscore theta minus 120. You can see a trend here. It's going to be falling through the currents. Next is going to be I underscore C current. It's going to be equal to the square root of 3 times I underscore CA. ICA underscore theta is going to be equal to I underscore B underscore theta. So IB theta is equal to 120. Switch to 120. Run it again. So we do get an error here. So we do have an unrecognized variable here. So I did write something wrong. And it's gonna be line 57. So you can see here we have an unrecognized statement. Oh, I did forget to add data here. It'll be okay. As you see, it's good to just run your code through, because if not, you're gonna be running through multiple errors. There you go. A good programmer will go through and write his code, his or she's code, they code, gender normed. As you go, you'll run it just to make sure you have no errors. If you write it all at once, you're gonna have problems. You have one semicolon, ruin your day. So now we need to calculate the parent power. So the parent power is gonna be just gonna equal to our v phase and I phase times by 3. So S is gonna be equal, which our parent power is equal to, this is the magnitude, is gonna be equal to 3 times v phase times I phase. And remember we got I phase, v phase is gonna be equal to our given VAB, which is 480. And that's how we stated later on, v phase is equal to v line, v line is equal to ABB, so 400 Ds. So now later on, when we do our I phase, we just do Ohm's law, v phase divided by Z, right? And then to get the angle, exactly the same thing as subtraction, right? Just because it's polar. So down here, we'll repeat that, but we are gonna do, in order to get the current, the angle, we're gonna be subtracting the currents again. So S theta is equal to V phase square theta minus I phase theta. Actually, realistically, I think they should be adding, but we'll just do this for here right now. I can fix it later. All right. Next. We need to convert the parent power to rectangular. Now we're going to do the opposite. We're going to just do A is equal to S times cosine D. This is cosine in degrees. If we just do cosine by itself, it will just be the radiant version of S underscore theta. Repeat that for B. That's going to be equal to S times sine D S underscore theta. Our S is equal to, oops, S rectangular, this is our total. Is going to go to A plus B times J. All right, so we're able to get a rectangular back to our rectangular form. So now we need to calculate the power factor. All right, so our power factor, sorry, I was just trying to make sure we're recording. Theta is going to be equal to theta of our power factor is going to be equal to V phase theta minus I phase theta. And that'll give us our power factor. So our power factor angle. So power factor is now going to be the cosine degrees theta power factor. And that should give us our value at the end. So theta power factor is our, oops, we messed up. We did not include theta. There we go. So equals 21, and then our cosine of that, our power factor is going to be equal to 0.982. All right, so I think our value is correct. So it's all ran through, but we do need to output it. This is really the cumbersome parts, is we got to print all of it. So we'll just fprint. Let's get really repetitive here. Fprint AB is equal to okay. So, oops, I did forget to write the correct fprint. There we go. Okay, so as we see, is AB is equal to, oh, oops, VAB. Okay, so this code what it does is basically allows us to, it's print the value to our command window, is VAB is equal to 4 decimal places over, so this is just 4 decimal places. In this case, we just can do 2 decimal places. Same thing goes for here, just want 2 decimal places. And again, it's just 2 decimal places. So it's gonna be equal to the floating output. This is just states that this is value is gonna be with this. Sorry, assign the angle, and then this is here. And then the new line. For first input over here is the F is going to be VAB and VA theta. So we're going to repeat that for next VAB, V line to line, V phase, VI phase, and then, so I'm just going to copy my pre-written code I had before to make sure it's correctly. I'll see here, same thing, V line to line is equal to this. So it's going to be V to line with the theta. V phase, exactly the same thing, is equal to V phase times V phase theta. So you just copy and paste this over to change this here. What's it equal to, and then change at the end what you want using. So we're just making sure that at the end we get the magnitude and the angle. Because remember how we separated them early on. It's a lot easier to do the calculations than them separate. So we're gonna create a new line. This can really cumbersome if I wrote this all at once. It'll take me hours. Next thing we do is we do VAN, VBC. So see here, it's gonna be just VAN is equal to this here. So exactly the same thing as before, just change it to different outputs. And then our VAC, this is going to be our calculating our sorry. VAB, where's it go? Oh, there you go, sorry. This is me calculating our load del connection, and then here was connecting our source Y connection. So source Y connection and our connection. Next, we want to get our currents. Same thing here. Currents, exactly the same, just repetitive. It's just its magnitude and its angle. Next, we're going to do our our IA. And this is constantly repetitive over and over, same printing thing. So I, A, B, see if you just pause the screen and go through and write the code down, it's very simple. It's not too complex since I ran out the first one. Exactly the same at the end. We are going to want to get our S, our theta, and our power factor. So we'll go through and just change everything to 2. So make our lives a lot easier and smaller. You go through and change yourself, but it's still the same thing. It doesn't do much, it just makes the decimal places a lot smaller. Instead of 0.00, maybe it's 2 zeros, it'll be 4 zeros. So you see our S here, it's just, this is modified. It's not having it doesn't have an angle, so it's just S rectangular. Theta is just the theta here, 4 decimal places, theta. Power factor equal to 0, and the power factor here. So we hit run. Oh, we do have a problem. Line 86. So we did not correctly state that guy. Okay, VC we did not say theta. There we go. Convert and run through. There we go. So we can see, let me just move the command window up. Everything ran through. So as you see, we have a VAB, a given value here. As we stated, VAB is equal to VL line. Our V phase is this. Oh, it's the angle here. This is given. Our I phase is this. Our VAN, VBN, VCN, VAB, VC, VBCA, IAB, IBC, ICA, IA, IB, IC, S, our parent power, our angle of our power factor, and an actual power factor. So as you go through, if you wanted to, depending on what the problem states, you can change it here. So this is it has to be it has to be what we stated earlier. That does need to be a positive sequence Y-connected source supplies a delta-connected load. You can go forth and change the voltage, and you can change the Z, and obviously the angle. But if it does change its connection, if it was say a delta source and a Y load, the MATLAB that we just wrote would not work. What we do need to make sure that we understand that this is for this exact problem. And if you do follow along, you will get a replicable. I'm sorry, you'll be able to replicate what I got. So there you go, all set. So I wish you good luck. Have a good one.